The next speaker is going to be Nidhi Rathi. Nidhi Rathi is a final year graduate student at the Indian Institute of Science, Bangalore, where she is working with Siddharth Barman and Marina Ghosh. She is a recipient of the prestigious IBM PhD Fellowship Award. Her research interests include computational social choice, algorithmic game theory, and optimization. Currently, she is working on the computational aspects of fair and efficient resource allocation problems. Today, Nidhi will give a talk, which is fair cake division under monotone likelihood ratios. Welcome.
Yeah, yeah. Thank you to the organizers for this invitation. Today, I'm going to talk about the fundamental problem of fairly allocating resource among the participating agents. So this is commonly referred to as the problem of fair division in the literature. And so today's talk would be based on joint work with Siddharth Barman, my advisor, and this work appeared in EC 2020. Okay, so in this talk, I'll focus on the algorithmic aspects of fairly allocating a divisible and heterogeneous resource, typically known as a cake. Such resource allocation settings have a rich history, and they've been extensively studied over multiple decades in computer science, mathematics, and economics. The resource, first of all, is divisible in the sense that it does make sense to fractionally assign it, and it is heterogeneous in the sense that it is not uniformly valued. Different agents value the different parts of the resource differently. Typical applications include the problems of division of land, spectrum allocation, or even scheduling time on a machine. The history of computational social choice and algorithmic game theory has seen a lot of impressive hardness results. Many of the central solution concepts that are supported by strong existential results turn out to be computationally intractable. This saga repeats itself in fair division literature as well, and that is, we have existential results for meaningfully fair allocation of resources in quite general settings, but on the other hand, we don't have their algorithmic counterparts. And in many cases, there are hardness or impossibility results that rule out polytime algorithms for finding such allocations. So we circumvent these algorithmic barriers, and we do it by looking at a specific family of instances. At a high level, we identify a rich class of instances for which finding a fair cake division is in fact polytime. And the key highlight of this talk is that we establish rare and interesting algorithmic results for cake cutting. So let me now jump and formally introduce the classical model of cake cutting. Here, the divisible and heterogeneous resource, i.e., colloquially referred to as a cake, this is modeled as a unit interval 0, 1, and what we're trying to do is to divide this cake among n participating agents in this fair division exercise. Also, the cardinal valuations are represented or expressed by valuation functions v sub a. So do note that the subscript a will identify the agent, that is v sub a refers to the valuation of agent a over the k. For some agent, his valuation can appear something like this, the figure which you are currently seeing on the screen. And also the density function will be referred by f sub a, but which is nothing. So v sub a of I is nothing but the under area of this particular density curve. Okay. And there will be some mild assumptions we'll be assuming on valuation functions, which are they're non-negative and they're all normalized to 1. That is, all agents value the whole cake at 1. They are divisible and also are sigma additive. Again, for some other agent, let's say some agent B, her valuation function can look something different, right? So the basic problem here is to divide the cake into n partitions by making exactly n minus 1 cuts on the cake. Every agent must receive a single connected subinterval of this resource. According to her valuation, an agent will have some value for this interval, and here again, I sub a represent the piece that is being assigned to agent A. Okay. So the entire exercise here is to find an n partition of the cake and assign exactly one interval, one connected interval to each agent in some fair manner. So while there is extensive work on non-contiguous fair division, where an agent can indeed, receive multiple intervals, but throughout we'll focus on a more challenging setting where each agent is assigned a single interval. In many applications, contiguity is a natural requirement of the problem, such as, let's say, in fair division. Okay, so this is the setup, but the fundamental notion of fairness, which we are looking in this particular line of work, is that of envy freeness. So this notion was first introduced by Foley back in 1967, and since then there has been an extensive literature of work in this particular area. And again, as the name suggests, a cake division I. So a cake division I consists of I1, I2 till In, these particular connected subintervals. Such a cake division is said to be envy-free if and only if each agent prefers its own interval over that of any other agent. That is, the notion of envy-freeness translates to saying that, okay, for some particular agent A, look at the piece that I assigned to her, which is I sub A. Her value for her assigned piece must be at least as large as her value for any other piece in the division I sub B. So do note that on both sides of the inequality, I am indeed invoking agent A's valuation. That is, he is not being envious of any other agent in the system. Okay, so this is the notion of envy freeness, and Stromquist in first of all in 1980 showed that it is possible to guarantee such an envy-free cake division in which every agent receives a contiguous piece of the cake. And Stromquist, so this existence came under very mild assumptions, and Stromquist's result, along with Su's topological proof of existence, is widely considered as a main or the cornerstone results in the area of fair division. Okay. Almost 30 years later, though, Stromquist himself showed that with respect to algorithms, you know what, we are out of luck, let alone exponential time algorithm or even doubly exponential time algorithm. There's not even a finite time algorithm. Though this result holds in the adversarial model, it is nonetheless a very strong negative result. And even, if you want to look at the algorithmic results for envy-free cake division, they remain elusive even if we relinquish the contiguity requirement. And the best known algorithm for this particular setting, where we do not focus on connected pieces and allow disconnected pieces, is a hyper exponential time algorithm given by Aziz and McKenzie in 2016. So even though envy-free divisions are guaranteed to exist, they are computationally interactable, and there are strong negative results with respect to computation. And so what we do is our main result is we circumvent all these algorithmic barriers by specifically looking at a broad class of instance, and we say that, what, for this particular large natural rich class of instances, finding an envy-free division is indeed polytime. Okay, so let me now jump into how into the technical part of this particular talk. So what we do is our main result is we are saying envy-free divisions can be computed in polytime for a broad class of instances, and the main takeaway here would be that the general existence, the proof of existence, uses heavy hammers of fixed point theory and Spurner's lemma. But what what we've been able to achieve is that for a large natural class of instances, the proof of existence can be reduced to a basic theorem of intermediate value theorem, and so for a rich class of instances, we have found that interesting properties emerge, and we are able to reduce the existence to one-dimensional fixed point theorem. And during the talk, it will be clear that how we are able to constructivize and develop an algorithm as well. Okay, so what is this class of value densities which I'm talking about? They are the ones that satisfy a particular property known as monotone likelihood ratios property. In a while, I'll define in a few slides what this particular property entails. But let me just mention here that there are well-known distribution families for which this property holds. So, in particular, if the density of your agents are Gaussian, then this result holds, and they satisfy the property of monotone likelihood ratios, and our results apply. And even in particular, if these densities are linear, then again our result holds too. So, in a way, our result, sort of in a single sweep, captures a lot of well-known distribution families, and we address all of these distribution in a unified manner and develop rare and interesting algorithmic results for cake division. Conceptually, identifying this particular unifying property of monotone likelihood ratios is an important contribution, and in the context of fair division, it leads to interesting algorithmic results. I'll define what this particular property is for just two agents first, and then I'll generalize it for a set of n agents. So, uh, so two densities f sub I and f sub j, they're said to satisfy MLRP if and only if their likelihood ratio, which is fj by fi. This likelihood ratio, if it's not decreasing over the cake, that is for over the interval 0, comma 1, then I say that these two densities satisfy the property of monotone likelihood ratios, right? And and when if you want to look for a bunch of a set of densities f1 f2 till fn, I say that all of these densities bear MLRP if and only the consecutive ratios, that is f of I plus 1 by f sub I, all these consecutive ratios satisfy the property of monotone likelihood ratios. So in particular, this property is quite simple to look, understand for linear densities. Just focus on these two densities, f1 and f2 over here, and it is apparent that f2 by f1 is before the intersection point, f2 by f1 is less than 1, and it keeps on increasing. At the intersection point, the ratio becomes 1, and after that, the ratio of f2 by f1 is greater than 1. That is, the likelihood ratio of f2 by f1 keeps on increasing throughout the interval 0, comma 1. So also, it is important to note that this particular property of monotone likelihood ratios is sensitive to the indexing of agents. That is what we are saying is these agents are indexed such that the consecutive likelihood ratios bear MLRP, right? Okay, and then at this particular point, I'll also want to mention that it's just not Gaussian, linear, exponential distributions, but also linear translations of log concave function also bear this particular property of monotone likelihood ratios. Okay, so let me now just describe how we are able to indeed compute NV-free divisions in such a setting. So for that, let me first introduce the concept of ripple divisions. So what does it say? It simply says that, okay, give me for a particular indexing of agents, these a set of points, so x0 starting from 0 till x1, x2, till xn equals 1, these set of points forms a ripple division of the cake if and only if what happens is the first agent is indifferent between the first and the second piece, the second agent is indifferent between the second and the third piece, and so on. And in general, ith agent is indifferent between the ith piece formed due to these set of cuts, and he's indifferent between the ith and I plus 1f piece. And again, do know that this is for a given indexing of agents. So that is where basically defining a new set of divisions. And what I'll prove is that under the property of MLRP densities, ripple divisions indeed induces NV-free cake division. And I'll sort of tell you how ripple division are they universally exist and can also be computed in polytime. And hence, NV-free division can also be computed in polytime for this class of MLRP densities, right? Okay. So towards that particular goal, what I'll do is uh, this particular property of MLRP, indeed, in the paper, what we show is it leads to a property of stochastic dominance per interval. And what does it say? It simply says that, first of all, what you do is, given a ripple division, you first assign piece one, the first piece to agent one, the second piece goes to agent two, and so on till the last piece goes to the last agent. And then what you do is just look at two agents, two neighboring agents, agent I and agent I plus one, and and what the property of MLRP guarantees is that, you know what, if you just look at these two particular neighboring intervals and normalize their densities, then agent I plus one values the right interval, which is the I plus one piece, more than what agent I is valuing this particular right piece. So having this stochastic dominance per interval, what we can show is under MLRP, ripple divisions indeed induces NV-free cake divisions. And what just to look for consecutive agents, it's what it says is that, you know what, for agent I, by construction of ripple division itself, was indifferent between piece I and piece I plus 1th. And then with the stochastic dominance per interval property, we can also prove that uh, agent I plus 1 also do not envy agent I. That is, ripple division mandates that there is no envy in between agent I and agent I plus 1. But interestingly, what we are able to show that that's just not the case. Even a stronger property holds true. That is, not just envy is not there in the consecutive agents, but also there is no envy overall. That is, what we show is that under MLRP, these ripple divisions induces envy-free cake divisions. And for the next step, what you can notice is that, given the first cut, the consecutive cuts are all pre-decided, because, you know, given the first cut, agent 1 will make a cut at x2 such that the first and the second piece are equally valued to agent 1. Now, given the cuts x1 and x2, agent 2 can make the third cut at x3 such that he is now indifferent between the second and the third piece, and so on. That is, what I can do is, I can write the last cut point as a function of the first cut point, right? And what we prove is that this function is a continuous function, uh, and therefore, via using intermediate value theorem, we show that there exists some first cut point such that the last cut point falls at 1. That is, you get a complete cut, right? And we also show that since now we have reduced the existence to one dimension, we show that this particular first cut point, such that the last cut point falls at 1, can be found via a simple binary search, right? So in total, what we are doing is, we prove that ripple division universally exists, and it can be proved via a simple intermediate value theorem. And then what we show is that under MLRP densities, ripple division indeed induces NV-free cake division. So in total, what we are having is NV-free divisions. They can be computed in polytime under MLRP densities, because the ripple division itself can be computed in polytime via a simple binary search. And hence, under MLRP densities, NV-free divisions can also be computed in polytime. So, uh, in to summarize my talk, I'd like to say that what we establish is that we kind of identify a universal property of MLRP, monotone likelihood ratios, which leads to a multiple positive results in the area of cake cutting. And in particular, we have efficient algorithms for finding NV-free cake divisions. We also give an alternate proof of existence for NV-free cake divisions under MLRP via ripple divisions. And we also prove that under MLRP, there is absolutely no trade-off between fairness and efficiency. That is, every NV-free cake division is indeed Pareto optimal. So Pareto optimal is a economic efficiency term. And and we also prove that under MLRP densities, there are multiple positive results for computing allocations that maximize various welfare notions such as social welfare, egalitarian welfare, and social welfare. So, finding a perfect division under MLRP densities is an interesting future direction. And it would also be really interesting to see that if we can generalize these results so that just for the densities that satisfy stochastic dominance. And again, identifying various positive results in other computational social science contexts through MLRP would be an interesting future direction. Yeah. Thank you.
Okay, thank you for this great talk. There is a question from the audience. Would it be possible to compute the price function and the CEI in this context?
Yeah. So, in the case of price function, we indeed have been working on this particular problem, and I think it is doable. But yeah, I we need a little more thought uh, compute a price function. And should be if I can do with Nash welfare. Yeah, so for the past couple of weeks, I've been trying to give an analog definition of MLRP in discrete setting, and in particular for settings what Vincent is asking for. But I think the answer is positive. But yeah, yeah. And for Nash social welfare in this particular paper, we give an FP task. But for social welfare and egalitarian welfare, we give a polytime algorithm for computing such welfare notions under MLRP densities. Yeah.
Okay, thank you. And I have a question myself.
Yes.
Is MLLP a sufficient condition for ripple divisions to be envy-free?
Oh, okay. So what we prove is that under MLRP densities, indeed ripple divisions are NV-free, but I don't think so the other way around is true. Yeah, I'm sure there are other conditions under which the thing might be true, but yeah, we have just identified one way. Yeah, it would be good. And okay, so my hunch is that the other way is not true. Yeah.
Thank you. Okay. Thank you for this talk and thank you for the answers.
Yeah, thank you. Thank you for inviting me.